Stoichiometry Part 3, Limiting and Excess Reactants. Our learning targets for today are to be able to identify the limiting reactants through stoichiometric calculation and then to calculate the excess reactant that remains once the limiting reactant is used up. Let's take the familiar idea of a recipe to introduce these terms. Given this recipe to make one blueberry mint smoothie, we have the ingredients listed as 1 cup of coconut milk, 1 cup of spinach, 1 cup of frozen wild blueberries, and 1 bunch of mint. Notice how you only need one of each ingredient to produce the desired smoothie as your final product. In order to make this smoothie, we get to see what ingredients we have available to us. This slide shows how much of each ingredient is available. We have 4 cups of coconut milk, 6 cups of spinach, 3 cups of blueberries, and 5 bunches of mint. We can call these ingredients our reactants. Combining these ingredients will give us our desired product. Combining one of each ingredient as shown in the recipe should allow us to make 3 smoothies. Can you see, based on the picture, why that would be possible? Let's talk about why we can only produce 3 smoothies given these ingredients. There are 2 types of reactants or ingredients every reaction or recipe can have: limiting or excess. A limiting reactant is the reactant that will run out or be completely used up in a chemical reaction. Due to this, it will control how much product is made. Once the limiting reaction runs out, the reaction will stop. This reactant will also produce the smallest amount of product. Based upon the ingredients available to us for the smoothies, which one do you think was the limiting one? Hopefully you guessed the wild blueberries. The excess reactant or ingredient would be any reactant that is left over or not completely used up in the reaction. So in the case of our blueberry smoothie recipe, the coconut milk was present in excess, as was the spinach and the mint. Let's take another look at the recipe to make sure you understand how the reactants combine to form each smoothie. These first 4 check marks show exactly how many of each ingredient went into creating the first smoothie or the first product. You can see all of the reactants exist in a 1-to-1 ratio, as does the product. The next set of 4 checks shows you what goes into creating the second smoothie. And the third set of checks goes into creating the final smoothie. The checks also help us keep track of which reactants are used up. The unmarked ingredients will help us understand how much of the reactants are left over. Take a moment to count up what is left over. Did your answer match these quantities? Let's take a look at another example. Observe the ingredients here to make 1 cheese sandwich. Given 2 slices of bread plus 1 slice of cheese, we should be able to produce 1 sandwich. Notice how the ratio of reactants differs from the previous example. 1 slice of cheese is used with every 2 slices of bread to make 1 cheese sandwich. Take a look at the provided reactants: 28 slices of bread and 11 slices of cheese. For this reaction to occur, we know that the reactants must exist in a 2-to-1 ratio. Since we have 11 slices of cheese and more than double that for the slices of bread, we know that we can have at least 11 sandwiches. The next question we have to address is, what is the excess reactant and how much of it will remain unused? Well, if we know that we've used up all of the cheese, then the excess reactant must be the bread. To determine how much of the bread is left over, we must subtract the 22 slices of bread used up in making the sandwiches from the original 28 slices of bread provided. That leaves 6 slices of bread left over or in excess. Let's take a look at a chemical reaction where hydrogen and chlorine combine to form hydrogen chloride. You can see based on the balanced equation that the reactants are present in a 1-to-1 ratio while the product has a coefficient of 2. Here is a molecular view of this reaction. On the reactant side, we have 6 molecules of hydrogen and 4 molecules of chlorine. Remember, both of these elements exist as diatomic molecules. The white molecules represent hydrogen and the green molecules represent chlorine. You can attribute the size difference to their difference in atomic mass. After the reaction on the product side, you can see that we have 8 molecules of hydrogen chloride. Notice how on the reactant side, you have fewer molecules of chlorine than you do hydrogen. That also means fewer atoms of chlorine compared to hydrogen. Once the 8 atoms of chlorine are used up, the reaction will stop. That is one way to determine that chlorine, in this case, is the limiting reactant. After the reaction, you can see that 2 molecules of hydrogen remain unreacted. This should indicate to you that the excess reactant for this reaction happens to be hydrogen. Next, let's consider an example involving masses instead of atoms and molecules. You can see on this slide that you have the same synthesis reaction given to you, but instead of atoms and molecules, you have quantities represented in grams. Here is the word problem with the same given values. Since we have 2 reactant quantities given to us, we will be expected to set up 2 different stoichiometry setups. Our goal will be to determine how much hydrogen chloride each of these reactants can produce. The one that produces the smallest amount of hydrogen chloride will be considered our limiting reactant. The other reactant will just be the excess reactant. This is an example of a limiting reactant problem. You know you're dealing with a limiting reactant problem when you are given quantities of both reactants. On the whiteboard here, we have our balanced equation. Since we are given the amounts of our reactants in grams, we will be converting that amount to moles, and then we will be using the mole ratio to convert to grams of product. Go ahead and set up your gram to mole conversion for hydrogen. Next, let's set up our mole ratio. Pause the video in between steps so you can practice this on your own. Remember to use the coefficients from the balanced equation for the mole ratio. Next, set up your mole to gram conversion for hydrogen chloride. Go ahead and use your calculator to solve. Remember to record your answer in significant digits with a unit and label of substance. Hopefully you got 1.80 times 10 to the power 5 grams of HCl. Let's move on and go through the next stoichiometric setup. Set up your gram to mole conversion for chlorine. Next, set up your mole ratio. And finally, convert moles of hydrogen chloride to grams of hydrogen chloride. Go ahead and use your calculator to solve for grams of hydrogen chloride. Remember to use significant digits, units, and label of substance in your answer. Let's examine our results. With 5.00 times 10 to the 3 grams of hydrogen, we can obtain 1.80 times 10 to the 5 grams of hydrogen chloride. And with 1.00 times 10 to the 4 grams of chlorine, we can obtain 1.03 times 10 to the 4 grams of hydrogen chloride. Compare the two results. Which value is smaller? You guessed it, this one. That makes this value our theoretical yield given these two reactants. You guessed it, hydrogen. Because we know that hydrogen is now our excess reactant, we also know that it will be left over at the end of the reaction. Let's examine how much of the hydrogen or the excess reactant is actually left over. Recall that we were given this amount of the limiting reactant. Through stoichiometry, we are going to calculate how much hydrogen or the excess reactant was used up in making hydrogen chloride to get to the 1.03 times 10 to the 4 grams of hydrogen chloride. The amount of hydrogen will be calculated in grams, so these are the steps that we will take to solve. For our first step, we're going to convert grams of chlorine to moles of chlorine, so go ahead and set that up here. Pause the video if you need to. Next, we will set up our mole ratio. Go ahead and set that up here. The balanced equation shows that we have 1 mole of each of the reactants. Next, we're going to convert moles of hydrogen to grams of hydrogen. Go ahead and set that step up. Remember to record your answer in significant digits with the units and the label of substance. The calculated answer comes out to 285 grams of hydrogen. This value represents the amount of hydrogen used up in the reaction. Do you know now how to determine how much hydrogen is left over? Think back to the sandwich example. Remember, we were provided with 5.00 times 10 to the power of 3 grams of hydrogen in the problem. We used up 285 grams of hydrogen in this reaction. To determine how much is left over, we simply have to subtract. Go ahead and use your calculator to do that now. This is the calculated answer. Remember to convert to significant digits. 4,720 grams of hydrogen, or 4.72 times 10 to the power of 3 grams of hydrogen, remain. Now you are ready to complete the rest of the limiting reactants worksheet.